I'm going to run through a quick example of solving complex circuit problems for whatever unknowns it is we're looking for. In particular, a way to do this without having to solve a system of a large number of equations through algebraic substitution, which can very quickly get messy. So let's start by looking at this circuit. So it's pretty clear that we can't use our normal methods of solving problems by breaking them down into parts that are parallel, parts that are series, and finding an overall equivalent resistance and so on, right? Because not a single resistor in the circuit can be considered to be in series with or in parallel with any other circuit in the system. There's a battery in between these, and these two resistors might have the same potential difference over here, but the other ends are going to be fixed by the potential difference of this battery and so on. So we use Kirchhoff's rules. We use the junction rule and we use the loop rule in order to figure out how to actually approach this kind of problem. Setting up the problem, I think, is usually not the challenging part, but actually following through and solving for whatever it is you're looking for, it can get really messy. So let's start. The first thing we should do is kind of identify the equations that we want to use. In other words, which junctions do we want to use, and which loops do we want to use. So we have a lot of choices. There are a lot of junctions. There's a junction right here, there's a junction here, there's a junction here, there's a junction here. So we actually have 4 junctions. If we write down the junction rule for all of these, they're actually, a lot of them are going to end up being redundant to each other. So in the end, we're not going to actually need all 4 of them. Likewise, we have a lot of choices for the loops we could use. There's the 2 sort of triangular loops inside this part of our circuit. There is the outer square loop. Then there is also the loop involving this outside battery. And then there is another loop involving this outside battery. And in fact, there's another loop that kind of snakes around like this. And there is another loop that does the opposite kind of thing. So we have a lot of different loops and a lot of different junctions. And if you write down the equations for all of them, I mean, it won't give you anything incorrect, but you'll actually have way too many equations, many of which tell you the same thing. And it's really easy to find yourself going in circles. So what we want to do is be a little bit systematic about it. We want to start by picking maybe a junction. The junctions tend to be a little bit easier. And anytime we pick a new junction, we want to make sure that whatever equation whatever equation we get is giving us new information. In other words, it has to relate currents. It always has to give us a new relationship between new currents. A good rule of thumb is if you write down a junction rule and it doesn't add an additional current to one you already have in a previous junction rule, it's not going to be very helpful. Before we start actually doing anything with equations, we have to start by identifying the directionality of the currents. Again, we might not actually know what the exact directions are. We can guess, and sometimes we can guess very well, but in the end it doesn't matter. If we guess wrong, the math will simply tell us that the current is negative, which means it's going the opposite direction of what we assumed it was going. So let's just pick a direction. So I'm going to say on this outer loop, let's say the current is going counterclockwise because this outer battery has a positive terminal on the top. And I'm going to assume, let's say, that all of the current is kind of flowing down. And I'm going to guess that the current is flowing sort of the correct way through this battery, and that the current is flowing in all of these directions. Next, we need to actually label each of our currents. We have to give them a number. So what I'm going to do is I'm not going to write them because it's become really cluttered, but I'm going to call the current through R1, I1, the current through R2, I2, the current through R3, I3, the current through R4, I4. Then I'm going to call the current through the first battery, I5, and I'm going to call the current through the second battery, I6. It's nice to have them labeled with numbers for the way that we're actually going to approach solving this. I could have written this as like IE1 and IE2 or something, but it's nice to just have them labeled in sequential numbers, and we'll see why later. So now we have to try to actually find our equations. Let's start by writing down some junction rules. So let's start with this junction right here. I like to start with junctions just because they tend to be a little bit easier. Not always, but often. Now, this first junction gives us our equation number 1. Equation number 1 tells us that I5 is an incoming current and is going to be equal to our outgoing currents I1 plus I2. Then we can write down our second equation, which we need another junction for. So why don't we go with this one? This junction tells us that we have an incoming current I1. We also have an incoming current I6. And we have an outgoing current I3. Then let's write down a third rule. And we will find that, well, why don't we pick this junction? Just keep going with junctions. We have an incoming current of I2. And then that has to be equal to the outgoing currents I4 and I6. There's one more junction that we haven't used, but we're actually not going to be able to use it. If I write this down, I'm going to get I3 plus I4 is equal to I5. Now, here I have I5 is equal to I1 plus I2, but I know that I can relate I1 to I6 and I3, and I can relate I2 to I4 and I6. And in the end, if I combine these three equations, it'll actually already give me the equation I would get from this junction. In other words, the fourth equation wouldn't actually provide any new information. That's always true. You can never use every single one of your junctions. At most, you can use all but one, and sometimes even that will end up double counting. So we are not going to be able to use this last junction, so we still need three equations, and that means we're going to have to rely on our loops. So why don't we pick some loops? I actually think I'm going to pick maybe these two triangular loops, and I'm going to pick both of them to go in the right direction. Let me make that. I'm going to pick both to go in the correct direction through the battery I6. So I'm going to go in that direction for this loop. And that gives me an equation, equation number 4. I'm going to plug in the numbers and I'm going to leave out the units. So if we start by going over across the battery, we go up by 6. Then we're going the wrong way across resistor R1 based on the current that I drew. Right, we're going counterclockwise, but the current is labeled as going that way. So that means we're going up in again in potential. So this is going to be plus R1, which is simply 1 times I1. And then we're going down the resistor 2. So minus 2 ohms times I2, and that's equal to 0. Then we can write down our fifth equation. Let's take this to be the other loop. And again, I want to take it going in the, I want to take it going the correct way through the battery. So we're going to take this loop going this way. And so once again, I start by going through the battery, which gives me 6. I'm going the right way down R3, so I subtract R3, which is 4 ohms times I3. And then I'm going the wrong way through I4, so I add 5 ohms times I4, and that gives us 0 because that's a complete loop. And then we can write down our very last equation, which means we need another loop. So right now you'll notice that I don't have this battery anywhere. It doesn't show up in any of these equations. And clearly the value of this battery is going to matter. So I want to make sure that I have at least one loop that encompasses that battery. I'm going to take that to be the, oops, I did it again. I'm going to take that to be the loop along this outer edge. And then I'm going to go down this sort of inner portion of the resistor portion of our circuit across resistors 1 and 3 back to here. And so when I write down the equation for this one, I get 12. I want to go this direction. It doesn't matter. I could have gone the other direction in any of these. It doesn't actually change anything. But I get 12 plus 12. I'm going the correct direction through resistor 1, so I get, no, that is not what I wanted to do. So I get minus 1 ohm times I1. I'm going the correct direction through I3, so I get minus 4 ohms times I3, and that is the complete loop, and so this is 0. So here I have 6 equations. The next step, the way that I end up, to make this easy on myself, I'm going to actually rewrite each of them. To do it the brute force way, I have 6 equations and 6 unknowns. So for example, here I have I5. Here I have, in fact, actually, this is the only place I have I5. So I can't plug that into anything yet. But here I have, for example, I3. I have I3 in terms of I1 and I6. So I can look for anywhere else I have I3, for example, over here. And I can substitute I1 plus I6 into I3. Now this is an equation between I1 and I6. Well, I can solve, for I6 over here in terms of I2 and I4. And here I have I2 in terms of I1. And I can slowly start to whittle down the unknowns until I left with one of them. Then, once I have one of them, I can use it to solve for more, and eventually I can get all 6 of them. But that process is terrible, especially, right, if I ask you to find the current through every single one of these, it just becomes a big mess. I don't want to do that. So here's the way that we should approach it. Start by rewriting each equation so that all of the currents are on one side, and all of the numbers, like 6 and 12, these are the things that really came from the batteries in the loop rules. I want to make all the currents on one side. I'm going to make that the left side, and all the numbers on the right-hand side. So for example, equation 1 becomes minus I1 minus I2 plus I5 is equal to 0. Then over here, I have I1 minus I3 plus I6 equals 0. And I can do that for the rest of the equations as well, just like that. And these are the equations I'm going to use going forwards. So let me just highlight them. And you'll notice that I wrote them in a particular order. I always put I1 before I2 before I5 in this case. I put I1 before I3 before I6 and so on. And all of the junction rules always have a 0 on one side because we're just relating currents to each other, so everything on the right is going to be 0. But then the loop rules give us terms that have actual values on the right. In most cases, not in all cases. If I had a loop that only went through batteries, then I would also have a 0 on the right-hand side. But in this case, all of my loops went through at least one battery, and so all of them end up with a value on the right. Now what I'm going to do is I'm going to rewrite these equations in a little bit of a different way. I'm going to take these equations and I'm going to write them into a matrix. So I have 6 currents, so I'm going to make 6 columns labeled by currents and 6 rows labeled 1 for each equation. In the first first column of the first row, I'm going to write the coefficient in front of I1 in equation 1. So that's -1. Then I'm going to write the coefficient in front of I2. That's also -1. Then I'm going to write the coefficient in front of I3, which is 0 because there is no I3. There is no I4 either. The coefficient in front of I5 is 1. There's also no I6. Then I'm going to do the same thing for 2. The coefficient in front of I1 in equation 2 is 1. And so that's a 1. There is no I2, so its coefficient is 0. It's I1 plus 0 times I2. I3 has a negative 1 coefficient. I4 is not there. I5 is not there. And I6 is 1. For I3, I have 0, and then 1, and then 0, and then minus 1, and then 0, and then minus 1. And for 4, I have 1, then I have minus 2, then I have 0, 0, 0, 0. And for the fifth equation, I have 0, 0, 4, because the coefficient of I3 is 4. Then I have minus 5, and then 0, 0, because there are no I5 or I6 in this equation. And I can do the same thing for the last one, which gives us positive 1. There's no I2. Then there's a coefficient of 4 in front of I3, and then 0, 0, 0. Now, this is a big equation. A big matrix. The way I'm going to do this is I'm going to write this total system of equation, the highlighted blue equations on the left, I'm going to write them all as a matrix equation. And the way that I'm going to do it is as follows. I'm going to multiply this matrix by a column vector where the first row is I1, the second one is I2, and then I have I3, and then I have I4, and then I have I5, and then I have I6. And the reason why I'm doing that is because if you remember your matrix multiplication, if I multiply this first row by this first column, if I do matrix multiplication, this is minus 1 times I1, plus minus 1 times I2, plus 0 times I3, plus 0 times I4, plus 1 times I5, plus 0 times I6. That is precisely the equation that I have over here. There is minus I1, minus I2, plus I5, and everything else is 0. So this first row times this column vector gives me equation number 1. The second row times my column vector gives me equation number 2. Third row times the column vector gives me equation number 3, and so on. Well, I know what I1 minus I1 minus I2 plus I5 is equal to. I know that when I multiply this row times this column, I get minus I1 minus I2 plus I5, but I also know that that has to equal 0. And so what I can do is on the right-hand side, I can write down the answer, essentially, to the other side of this equation. So that's going to be another column vector because each of these equations has a right-hand side. So the right-hand side of this is 0 because, again, this row times this column is the left-hand side of this equation, and that's equal to 0. I can do the same thing for the second equation. This row times this column is the left-hand side of equation number 2, and that is also equal to 0. The third one is also equal to 0. The fourth one is not equal to 0 anymore. Now I have the voltage of the battery showing up, and so that gives me a 6 over here. This one also gives me a 6, and this one gives me a 12. Now you might think, okay, great, you've just rewritten your system's equations, and now you've done it with matrices, and you've made everything more complicated. But I haven't, because matrices are wonderful. I'm not going to teach you the math of how to do this. But if I call this whole matrix M, and because this first column vector is a vector of all my currents, I'm going to call it I'm going to label it I. And this actually represents voltages effectively, so I'm just going to call this V. I'm looking for I. I want to know what are the values of I1, I2, I3, and I4. So I want to solve for this. Well, I'm going to move this thing over so I have more room. And here's what I can do. If I can multiply the left-hand side of this matrix by another matrix so that I get 1. I get the identity matrix, which I'm going to call this the inverse matrix of M, where M inverse times M is equal to 1. Then I have to multiply the right-hand side of this expression by the same matrix. So let's move this over, and I am going to write the inverse of M. To make it a little clearer, basically, on the left-hand side, I have M inverse times M times my column vector that's full of the current that I'm looking for is equal to M inverse times V, which is a vector that I know. And since M inverse times M is simply 1, it tells me that my currents are equal to the inverse matrix M times the vector V. And I already know what V is. I know all the elements of V. And M inverse is something that I can find because I know the matrix M. So if you've taken a linear algebra course, or maybe you learned how to invert matrices in pre-calculus or something, then this is something you might already know how to do. I'm not going to go through the math of it because I don't expect you to actually do this process by hand on an exam or anything. Instead, I'm just doing this so you have an idea of where this is all coming from. What I recommend is to use your calculator to do this. Your calculator can invert matrices, or alternatively, you can use your calculator. You can use the matrix function in your calculator to solve a system of equations. And so there are instructions on the Google Classroom that you can follow for most, I think, the common calculators that most of you probably have. If it doesn't apply to your calculator, I encourage you to look up instructions for it. And at this point, you use your calculator or you use a computer and you evaluate I. The answers will literally come out. So for example, I did this myself, and I found that when I solved this matrix equation, I found the vector I came out to be a vector with the first value was 228 over 103. The second value comes out to 102 over 103. The third value comes out to 252 over 103. The fourth value came out to 78 over 103. The fifth was 330 over 103. And the last was 24 over 103. And this first quantity is I1. This second quantity is I2. The third quantity is I3. The fourth quantity is I4. The fifth quantity is I5. And the sixth quantity is I6. So now I have my answers. All of these are the answers to the problem, where since I made sure that all of my units were in ohms, volts, and amps, each of these are currents measured in amps. And so I found the current through every part of my circuit. And if I bring back my original circuit, I now know everything. I know all the voltages of the batteries because I was given those. I was given all the resistances, but now I also know the currents through every element of my circuit. So this is the easiest way to go about this. And the key is really in this part over here. So once you've written out your system of equations, if you rewrite them like these highlighted blue terms with all the currents on the left and all the values without currents on the right, all of the coefficients of the currents can be used to construct a matrix of coefficients. All of the values on the right can be used to construct sort of the answers to those equations. And we can represent the unknowns as a column vector of all of our unknown currents, and we can solve this whole process and we can find whatever it is we're looking for. Now, this actually works too if I have values in here. If, for example, if I'm given some of the currents and I don't know some of the resistors, I can still do this process. What that means is I would have some values populated in here, and I would have other values not populated, or rather, maybe, for example, I don't know what one of these resistances is, so maybe instead of having a 1 here, or that's a bad example because that was from a junction rule, instead of having, for example, a 4 here, maybe this is R3 because maybe I didn't know what R3 was. And maybe this would also be, again, R3. Now, the process of solving these things, depending on how you set it up, your calculator can still probably make it work. But most of the time that we're dealing with these kinds of problems, we're looking for the currents and we're given the rest. But in principle, the same process can be used to find missing resistors and not just missing currents. I hope that is helpful. Again, please look up the instructions on how to do this on your calculator. I don't expect you to do this whole process manually. If you do know how to use matrices and if you do know how to invert them, you always can. There is absolutely no rule against doing that. All right, see you next time.